volumes with a cylindrical shell. Suppose I have a function y equal f of x. And I'm going to take it from A to B, and I'm going to rotate that about the y-axis. As it rotates, it's going to create an identical shell. So something like this. Okay, close enough. No, except for this one, I want it to be right there. How about right? No, that's fine. So as this rotates, it's going to create this shell and cylindrical because those are cylinders. Now what I'm going to do, I'm going to break this up. I'm going to go to x1, and as this rotates, I'm going to look at that piece. Then I'm going to go then so looking at this volume, what I'm going to do, I'm going to say the volume is going to be V1 plus V2 plus V3 plus V sub n, in which this is of course volume 1, and volume 2 would be the bluish one right there. So I take one of those, let's say I take the blue, and I'm looking at this. The red, the first one, looks like this. Now, to find the volume of each of those, what I'm going to do, I'm going to cut this open, and it's going to look like this when I put it out flat, in which this thickness is delta x. This height is f of x1. If I call this x sub 0, that is x1, that is x2, that is x3, and that is xn. Now, this right here is the surrounding of this, and the surrounding of a circle is 2 pi r. But r, if you look at the radius is really x1. If I do the same for the blue, if I take the blue and I cut it open, it's going to look like this. In which this is delta x, this is, the height is f of x2. And this is 2 pi times the second radius in this case. The radius is x2. So this would be 2 pi r1 f of x1 delta x, plus for the second it will be 2 pi r2, which is x2, I should have said that's x1, f of x2 delta x, plus, and when I get to the last one, that is 2 pi x sub n f of x sub n delta x. So I would say the volume is roughly the series I equal 1 to n 2 pi x sub I f of x sub I delta dx, where this is really, you know what, probably I'm better off keeping that as r sub 1, r sub 2, r sub n, and make that r sub I, because it's going to vary from problem to problem. In this case, it is x1, x2, x3, and so on and so forth. And if I wanted to get an exact, if I wanted this to be, so this is roughly an approximation, because the height is varying slightly. You notice the height is tilting, right? So it's not really flat. It's kind of tilted. If I want to find the exact volume, I take the limit as n approaches infinity of the series I equal 1 to n 2 pi r sub I f of x the dx. I rushed by putting that. And that would be the integral from a to b of 2 pi times the radius times the height dx. So keep in mind how this works. This is the height, and if you're running vertically, that's top minus bottom. If you're running horizontally, that's right minus left. This is the radius, and this is the thickness. And that's pretty much it. So, glancing at the first problem, now what's the catch? In the previous section, we picked our rectangles perpendicular to the axis of rotation. In this case, do you see we're picking our rectangles parallel to the axis of rotation, and the cylinder is right in front of you. You need its height, you need its radius, and pretty much you're set. Here's a problem. Y equal x squared. Y equal x squared. Oh, I shifted everything, so now everything's going to be off. Even though I worked hard to center those, but that's okay. Y equal x squared. 0, 0, 1, 1, 2, 1, 2, 3, 4. So the graph looks something like this. And it's cut off at, use the cylindrical shells to find the volume generated by rotating the region bounded by the given above the y-axis. Y equals 0. This is y equals 0. X equal 1. And x equal 2. You know what? I'm going to rescale this. So this is 0, 0, 1, 1, 2, 1, 2, 3, 4. So I'm looking at this between x equal 1 and x equal 2. I'm looking at this region. And I'm going to rotate that about the y-axis. So pretty much it's going to create an identical piece like it. I love it when these things happen. Okay. I'm going to shrink this down. I want you to see there. So y equal x squared 0, 1, 1, 2, 1, 2, 3, 4. There we go. We're running this from 1 to 2 and y equals 0. So the region is right there. And this is going to create an identical copy like it to and that's going to be the image. Remember, everything's based on the original. So if I pick my rectangle parallel to the axis of rotation, there's the actual disk. Volume is going to be the integral from x equal 1 to x equal to its dx, and 2 pi, the radius. Well, glance at this and tell me what the radius is. This is the deal. You always run from the origin, always, to the rectangle that you picked, and you call that an x if you're on the x-axis, and you call it a y if you're on the y-axis. So, if you look at that, isn't this radius actually the x in this case? And what's the height? The height is top minus bottom. The top is x squared minus 0, which is x squared. And there it is. And I'm assuming you could integrate all of those, so the integration I will leave to you as an exercise. Here's another problem. X into x minus 4, so 0, 0, 1, 2, 3, 4, and the vertex is at negative 2, 2, negative 2. A parabola that looks like this. Y equal negative x, 0, 0, 1 down, 1 to the right, 1 down, 1 to the right. So the line looks like this. And let me alter that graph slightly. So the graph, let's say it looks like this. That's the region that I want. I'm going to rotate this about the y-axis. So isn't that going to create an identical piece like it right there? And that green is going to create an identical piece like it right there. And that will be the image. So if I pick my rectangle parallel to the axis of rotation, delta x, there's my cylinder. Volume is going to equal the integral from, and it's with respect to x, x equals 0 to x equal, I'll get that in a minute. I'm going to go from the origin to wherever that is, call that an x. Isn't that the radius in this case? Right minus left. So 2 pi, the radius is x. The height is top minus bottom. The top equation is, if this is the x, you want this y equal always. So negative x is the top. And what's the bottom? Wouldn't that be x squared minus 4x? So this is the height, this is the radius, this is the thickness. Now what's left? Where does x squared minus 4x equal negative x? That's when x squared minus 3x equals 0. X into x minus 3 equals 0. That's it. X equals 0 and 3. So that's where these meet. This should be a 3 at 0. The graph is not drawn scale. Integrate that, and there's the volume. And what if I wanted to take y equal cube root of x? We know what that looked like. That's a graph that looked like this. X equals 0 and y equals 3. So we're talking about a region that looks like this. Okay, y equal x cubed. X equals 0 and y equals 3. Let's say that is 3. This is the region we're talking about. I want to take this and I want to rotate this about the x-axis. Doesn't this create an identical copy like it? Again, this is not drawn to scale. And it'll give an image right there. And I'm going to pick my rectangle, so volume is going to be the integral. I'm going to pick my rectangle parallel to the axis of rotation, always to the original. So that's 2 pi. And I'm going to always run from the origin to wherever this thickness is. If it's along the x, I call it x. If along the y, I call it the y. So the radius here happened to be a y. And the height is right minus left. The right equation is, so this is a dy. If this is the dy and y equal cube root of x, you want x equal y cubed. Y cubed minus 0. And the limits are going to be in terms of y from 0. Where does the cube root of x? Oh, that's simple. To 3. I don't have to solve anything in this case. And there it is.